Okay, let's keep going. Next example, same section, 8.1 still. We're going to do example 2. Notice this is an indefinite integral, so right away we're going to have a plus c at the end of our answer. So if you want to, if you know, like you might forget that, just like make yourself a note. It is an indefinite integral, so we need a plus c on our final answer. Okay, so a lot of times with math, and it's not just calculus too, or any calculus, it's just math in general. You have math, what I like to call tools. So math tools, things you've learned in the past and things that you're going to continue to learn that you're going to use and refer to. So I think of them as tools because I need this tool to do this job. In this case, the job is this antiderivative. So math tool. What tool can I dig into my toolbox and grab that's going to let me figure this antiderivative out? Let's find out. Here it is, complete the square. Okay, so that's something that you learned in algebra. Now, I know you might not remember it, so I'm going to walk you through it. If you remember it, that's good. You can kind of fast forward a little bit and see if you can, or pause it really, that'd be better, and see if you can get the answer before I do. Now, we can't necessarily use u substitution here. We did in the last example, and the reason why we don't want to use it now is because the derivative of our real only choice would have been this radicand. The derivative's not there. If I pick the radicand, 8x minus x squared, the derivative is not somewhere else in this integrand. So we're going to complete the square on the radicand. So I'm going to rearrange it. So I'm going to say negative x squared plus positive 8x. So when you're completing the square, you do need to factor out any coefficient other than 1. So that negative 1 needs to come out. So this becomes x squared minus 8x. And then when you complete the square, you are literally completing something that's incomplete. So you are adding what I like to call the missing piece. You're making this complete, a complete perfect square. Now, because we don't want to change this technically, we have to take away whatever we add. And that's because it's going to look different, but it's officially the same quantity, the same expression, if we add and take away the same thing. Now, the missing piece, it's always the same process. You take half of your linear term, so in our case, half of negative 8, this coefficient on the linear term. So linear meaning like first power here, first degree, exponent of 1. Negative 8 is a coefficient. You always take half of that and you square it. Every single time, half of the coefficient on the linear term squared. And so that's going to be negative 4 squared. So we're missing a 16. And whatever I add, I also take away. Okay? Real quick, if this helps you remember, completing the square, it's named that because, of course, you're making this a perfect square trinomial, but you can actually draw yourself a square. So half, just remember you need half of this. So half of negative 8 is negative 4. And so if you times these, the missing piece is 16. All right. Now, why do we do that? Why do we complete the square this way, and why did I want to do this in the first place? It's because what we end up with, we have negative out front, x squared minus 8x plus 16. I'm going to go ahead and take out this other 16. This was just like a necessary because I have to keep my expression the same. So minus and minus, there's a plus 16 in the back here. Why we complete the square is because of what we get. This is a perfect square trinomial, and what that means is it factors as something squared. So this is a perfect square when it factors. The negative still out front, the plus 16 still in the back. This factors very nicely as x minus 4 quantity squared. Real fast reminder, the factoring for your perfect square trinomial, if you didn't recognize it, you can always take a shortcut. It's always this number back here, right before you square it. I didn't show the work, but this was a negative 4. So half of negative 8 was negative 4. Then we squared it. This number here always goes in your factor, every time. All right, back to the calculus side of this. So this was all kind of like our side work here. So I'll kind of box in our side work here. All right, now that's beautiful. Here's where we're at. So I'm going to take my radicand down there and I'm going to rewrite it using our factoring that we came up with. And I'm just going to put the dx in the back. I like to do that. And what was the radicand down here is now going to be rewritten. I'm going to put the 16 first, minus x minus 4 quantity squared. Okay, why did we do that? So I'm telling you that was the right choice, that was the tool we needed, but what was the point? The point is, this is actually very familiar looking. This is on your table, 8.1. So I'm going to pull up the table real quick, we'll figure out what does this look like, and then we'll jump right back here to the answer. So from your table 8.1, this was one of your antiderivatives, number 18 on the table. Since we're kind of just barely remembering how integration works, we're getting back into it, you can memorize it for this, or just reference the table for now, and then in 8.4, section 8.4 coming up, we'll work on how to figure this out, okay? So what you want to just recognize is, what do you have that matches? You have 1 over, or dx over, a square root. The first term is something squared, so this is a squared. The second term is something squared, in this case u squared. I just switched it to u. I know the table said x. I switched it to u just to not get confused with this x. So if a squared is 16, then I know that a is 4. If u squared is x minus 4 squared, then I know that u is x minus 4. And then I can jump right from here, this antiderivative, and I know the answer from my table. So this is sine inverse, u was x minus 4 over a, which was 4. Don't forget the plus c. Final answer. Okay. So if you are familiar with trig substitutions, I wouldn't just go from here to here. I would show more work. But one more time, we will learn that in the very near future in section 8.4. But for now, we're just jumping from here to here.